and answer questions. So now that I've brought everybody up to speed to the latest rules and regulations, let us begin. Thank you. And by the way, there's snacks and refreshments on the
help
back.
yourself to snacks Thank you for that introduction.
And for your sacrifice and hard work. It sounded like way too much red tape.
My lawyer, everybody.
Yeah.
Okay, I won't say more about that. Getting back to physics, or machine learning specifically. Okay, I'll begin. So thank you everyone for showing up and coming to my talk. I want to begin with the title of my dissertation, which is written here. And we're just going to jump in by first exploring what it all means. Okay, so let's see, we have my clicker here. All right, so I don't think machine learning needs much introduction, but one common criticism of machine learning is that the methods are rather opaque, that it's a black box, that you don't know why what is happening is happening. The field of interpretability research seeks to try to elucidate this black box and try to figure out what's actually going on. And this comprises a lot of different methods. There's not just one thing which is interpretability. And there are a few points in our work where we have done things which I would say we always try to understand what is happening in our models. And we try to do different things. We'll get to this later. This is something called symbolic regression, which is a very interpretable model. We'll get to those later. And generally, we're applying these methods to two different parts of physics: particle physics and exoplanet atmosphere inference. Okay, so I'm going to start with a little timeline of everything I've ever done in grad school. So first of all, I started here in the fall of 2018. Everything. Everything. Okay, I guess it's not everything. It's glossing over some details like what happened there. But the interesting stuff. In fall of 2019, I joined the Machev group. And our first project, so these are going to represent all the different projects that I've been a part of that we've worked on. Our first project, and there's COVID for reference, was wombling on spatial data, which is this idea, we wrote a paper on it. And the idea is that new physics manifests as a part of some sort of space of measurements with a higher density than the surrounding area. And so finding this new physics can be reduced to just finding boundaries between high and low density regions. So you can see some plots with high density on one side, low density on the other side, and attempts to find the boundary of this region. So I've already talked about this in my qualifying exam a few years ago. And this comprises chapter 2 of my thesis, but I will not talk about it more here today. After that, we worked on another project, which investigated uncertainties associated with data sets that were augmented by GANs. So GANs are a very interesting machine learning architecture, which allows you to generate more data that follows a certain distribution of the training data. But we found at the time that some people were trying to use this to augment data sets that were not big enough. And we proved some interesting bounds on how much this can actually help you. And essentially, we figured out that what it generates cannot statistically be better than what you put in. You know, there's no free lunch. Again, I will not be talking much more about this in this talk. Another thing we've worked on is the Earth movers distance. This is it's a statistical distance. It's a way of measuring how similar two distributions are. And it's useful if you want to know, for example, you measure something and you get some sort of distribution, and you have some theory that predicts something, and you say, did I get what the theory predicted, or did I get something else? So this is a very useful metric. I will also not be talking more about that in this talk. So we've done a lot of things, and not all of it can be fit in. One other thing which we did, which we will see will also not be fit in beyond this slide, is quantum computing. So quantum computing is a very interesting topic. There's essentially two types of quantum computing. There's circuit-based quantum computing, which is with the gates and things like Shor's algorithm. And then there's another field, which is adiabatic quantum computing. In adiabatic quantum computing, what you do is you have a whole lattice of spins, and you encode the problem that you're interested in into the interactions between spins, and then you adiabatically cool the system, which just means very slowly, and it gets to the ground state. And the idea is that if you set up your problem correctly, if you set up the weights to represent the problem, you can do it in such a way that the ground state, meaning the lowest energy state of the system, what it reaches once you've cooled it adiabatically, this tells you the solution to the problem you were asking in the weights. So one thing I'm very proud of is we formulated the Earth mover's distance as an adiabatic, as a quantum Hamiltonian. So this is a Hamiltonian that you can define for an Ising model, and you can put in all the different distances here. Those are the rows, and that's what defines the problem that you're interested in. And the thing will spit out the answer, which is the optimal transport thing. So this again, I will not talk more about. So this is some interesting things we've done. This brings us all the way up to, it looks like this is around 2022. Now in 2022, up to this point, you just heard from the boss, Dr. Konstantin Maciej. In 2022, something happened. We came under new management. So we were working on all these different things, and we were very interested in applying machine learning to things. And Dr. Maciej was showing us some papers where people were using machine learning for the purpose of exoplanet atmosphere inference, which we'll get to in a second. And so basically what happened is she took over as the boss, and what ensued was an explosion of received research. So, okay, so the problem of exoplanet atmosphere inference, so this is called transit spectroscopy. Let me paint the picture of the physical situation. So you have a host star with its planet, okay, some planet outside the solar system, and the basic idea is that most of the light will just go from the planet, and some of this reaches us directly. So imagine we're off over here to the right side, and most of the light from the star just hits us directly. Some of the light gets blocked by the planet, and we don't see it. Okay, if the planet comes between us and the star, that's what a transiting exoplanet is. But the really interesting part, that's already interesting. So this allows you to detect exoplanets. But some of the light actually reaches us after passing through the atmosphere of the planet. And when it passes through the atmosphere of the planet, it gets scattered and absorbed in ways that depend on the planet's atmosphere. So from our point of view, the planet's going around, so here it comes, it's about to cross in front of the star, it transits the star, we perceive, this is the overall intensity, so it's at 100% now, and then when the planet passes again, you're going to see the intensity drop. So this is intensity with respect to time, but there's more to the picture than this, which you should guess from the inclusion of the word spectroscopy here. So we can look at it from a new perspective. We have data that we can measure, which is about wavelength. So we look at it from this perspective, and we see that there's actually a rich structure here. In particular, we're interested in this quantity. How much of the light got blocked out by the planet and the atmosphere? So let's just measure this thing. So we want this line here, which is how much was blocked off as a function of the wavelength. And we can relate this to what we call the effective radius. So, excuse me, the atmosphere makes the planet seem a little bit bigger than it actually is because it does a little bit more absorbing than the bare planet would. So this effective radius is what we're interested in. We can write down an approximate analytical formula for this effective radius. And this depends on all sorts of parameters of the exoplanet. So the temperature, the pressure, the atmospheric constituents, etc., the mean molecular mass. This is an approximate formula which was derived by some people in the literature. So what we did is we took some data, and in this paper, we employed something called symbolic regression. And what symbolic regression does is, unlike something like polynomial regression, where you try to fit the function just as some polynomial, symbolic regression opens the space of possible functional representations to more complicated things like sine of x squared or something like this. Like you have the freedom to make these complicated expressions. And as you can see, this is such a expression. You know, there's a log in there, there's an Euler-Mascheroni constant, there's some special function. And so we were able to rederive this formula using symbolic regression. But that's not all we did in this paper, actually, because that alone is kind of, well, okay, so the best part is that the one way we did this was by using dimensional analysis to reduce the space of this symbolic regression search process. So when you're making a formula, you make it out of variables. So you can have all these operations, but at the end of the day, they're operating on some variables that you feed in. And in this case, we saw there were a whole bunch of different variables. Here's the 7 variables we're looking at. We actually found that you could reduce this using dimensional analysis to only 4 variables because they can't all enter into the formula in a dimensionally incorrect way. You can't add a mass to a length. You know, that would make no sense. So by using dimensional analysis, we can reduce the space to only the dimensionless combinations that are possible to make. One cool thing about this is actually last summer I was at ICML, of the International Machine Learning Conference, and I was talking to some researchers from Facebook, and they were working on this problem of symbolic regression. And it just came up in conversation that we were both working on this relatively obscure thing. And I showed them this paper, and they were very interested because they previously didn't realize that this dimensional analysis technique could so elegantly reduce the problem space. They thought that this was something you had to figure out on the fly, but it turns out this is something physicists have always known. So maybe a nice example of something physicists have to contribute to machine learning. So that's the dimensional analysis part. The other main result of this paper is we found that there are certain degeneracies. And by degeneracy, we mean something where it could be any one of these combinations, but they make no difference to the final product, which is the effective radius as a function of the wavelength. So we found, that's what these lines are here. There's little triangles and lines. And a couple of the simple ones that we found are, for instance, that in this analytical approximation, it makes no difference if you say increase the temperature and the mass simultaneously. Increasing the temperature has the effect of puffing up the atmosphere. Increasing the mass has the effect of kind of making the atmosphere smaller because of gravity. So those effects cancel out if you scale them in this way. Likewise, you can increase the pressure, but decrease the kappa, which is the cross section. That's a little less intuitive, but so we found these things, and these are very useful when you're trying to do an inverse problem. You're trying to figure out, okay, I measured this effective radius. What were these parameters? We are saying that's actually not a very well-defined problem. If you have any combination of these, you know, I can scale these up any way I want. These are all equally good as possible parameterizations. So you should take this into account when you're trying to do this inverse problem. You should be aware that such degeneracies exist. Okay. Oh, and we have another paper which is being written, which actually does the same thing but on a realistic model. So this is all a toy model, so it's very nice, but maybe these aren't realistic. Maybe these don't transfer over into the real world where things aren't quite as nice as we assumed that they were. What we found is that essentially they do. So that's not in the dissertation because that's not completed yet. Another thing we did with exoplanets is, so like I said, when we originally started this project with exoplanets, we found that there were a lot of people using all these machine learning techniques without really stopping to ask very fundamental questions. So we have a paper which is all about just doing unsupervised learning to try to figure out the structure of this space, try to figure out what would be sensible ways of pre-processing the data and such. And surprisingly, this had never been done before. And when we did it, we actually uncovered here in the PCA basis some interesting structure. And each of these weird branches of this thing corresponds to a different each point on here corresponds to a simulated atmosphere with a different composition, and each branch corresponds to an atmosphere dominated by a different component, so water or methane or so on. So we noted some of these interesting things. In another paper, we proposed a method for using all this stuff we've figured out to to try to actually invert it. So basically, this is a way of pre-processing all this data, and actually, in the analytical approximation, this works perfectly. Like, this is the perfect way of inverting things. So it remains to be seen in the slideshow whether this actually would work on the real thing. So then, while we were working on this, we found out about something called the Aerial Data Challenge. So this was something that was part of NeurIPS 2022. And what Aerial is, it's a space telescope that's going to be launched, I think, in 2028. And the collaboration put on this hackathon, essentially, where they challenged the community to develop a method of taking the spectra and recovering the composition of the atmosphere, the temperature, and so on, which is exactly what we were working on. So we were eager to work on this. So we entered, and surprisingly, we actually won first place. Perhaps not so surprisingly, if So yeah, there were actually 200 people competing in it, and we got the $2,500 prize, and we are also publishing a proceedings paper. So we're contributing to this paper. This is an excerpt from the paper, which is actually going to be submitted 2 days from now. In the excerpt, the organizers wrote this. They said that the people with expertise in astronomy, that's us, we were doing lots of pre-processing, and that the people who only had AI backgrounds were not using such domain knowledge. The former approach seems to make the learning task easier and allows for more flexibility in the learning approach, as demonstrated by yours truly. So, so this also I should give credit to the whole team, of course, because this is not me. This is Roy over there and you, those two especially. Yeah, oh yeah, you can see the picture. Okay. So, yeah, thank you. I also have on here some independent work I've been doing, because at some point I want to actually get a job with all this, so I've been studying some other things on my own, but I'm not going to talk much about that. Okay, that's sort of all the background. This brings us almost up to present day. So we have another project, which I'm very excited about. This project is the attempt to find symmetries in with machine learning. So let me just first say that a symmetry we know as something that leaves some quantity unchanged. So for instance, there are symmetries of a square. You can rotate it by 90 degrees and that leaves it unchanged. They come in two flavors. They can be discrete like that. I can only do 90 degrees, 180, 270, etc. Or they can be continuous, like the circle. You can imagine I could rotate that at any angle and it would still be the same. So these continuous symmetries are very important in physics. This is the foundation of the Standard Model, and Noether's theorem is like one of the most beloved results in physics. So formally, they're described by, these are called Lie groups. So if you have a continuous group of symmetries, that's called a Lie group. And the point is that they all satisfy that there's some conserved quantity. So you define some conserved quantity, and there is a symmetry associated with it. By the way, Noether's theorem is the opposite of that. It says, given a symmetry, there exists a conserved quantity. So we wrote one paper on this in January. Then we wrote another one 2 weeks later, right before the deadline to submit to ICML, which is, again, the machine learning conference. And then in February, we wrote another paper, and I'll get to all of these. And this brings us to the present day. And very soon we will hopefully be publishing the 4th paper on this, and we have a whole bunch more in the pipeline, which we cannot stop working on, because it's just so much fun, because we keep getting so many cool results. Okay, so let me talk a little bit about what's in this paper first. So in this paper, what we do is we take as an example of something that might be conserved. So I'll refer to this from now on as an oracle. So it's something that you can just apply to data and it gives you a number or a set of numbers, okay? So it's just some function. So as my oracle, I'm gonna take this function, which is the length of a vector, okay? My points are vectors in some space, so it's the distance to the center, to the origin of the space. So we might ask, this is the simplest thing we could think of, let's say, what are the symmetries that correspond to this oracle? So what we're going to do is we're actually going to create a whole data set. And in practice, this is just a bunch of points sampled from a Gaussian. It doesn't really matter their distribution. All that matters is that they be somehow representative of the symmetry. You just have to have a lot of them and a diverse set of points. And then we're going to take some hypothesized transformation, okay, propose some sort of way of changing these points, and then we're going to say, did the oracle change? So in the case of this oracle, we know the conserved what transformations should preserve this oracle. What transformation should preserve the length of the vector? Rotations. So a rotation preserves the length of a vector. I could just rotate it, that's not just scaling point. So in this case, these were actually derived by our method, but we also know them sort of a priori, so it helps to check our intuition. So we have intuitions we can check. Later on, we'll generalize to more complicated oracles than this. So let's talk about how we're going to do this exactly. So Lie groups formally are described. You can get any transformation by exponentiating combinations of these generators, okay? And the generators are like the 3 rotations we saw about each axis in the last slide. That's something we know beforehand, but we're not actually going to put that information into the model, okay? We wanted to generalize beyond rotations, so that would be cheating to just tell it that information, okay? So we're going to take our generator to just be some arbitrary linear transformation. So it's just some way of changing the data. And from now on, I'm going to represent this matrix with this block image, okay? So each one of these, I don't know if you can see the color bar there. So that's 0. So white is 0, and then these are just different numbers in a matrix. This is some random matrix. And so what we're going to do is we're going to take our, okay, so let me finish saying this. Any transformation can be represented as this exponential of these combinations of transformations. But locally, all it is the identity map, which means you do nothing, plus epsilon, which is small, times the generator. So you do nothing plus some small thing. Okay, that's the local symmetry. So we're going to parameterize these G's, and the way we do it is in PyTorch. So this is mostly apparatus for making a whole list of these generators. The generators are implemented as linear layers with no bias, because that's just a linear transformation. And you can see here that this is exactly what the theory says. So this is here, we're putting in the form we want it to come out in. Okay, so we're going to parameterize our thing this way. And we pick something, which some oracle, which we want to find the symmetries of. So as we said, we want to find the symmetries of keeping the length the same. So the recipe for doing this is we're going to pick some number. This is something we put in at the onset. How many of these transformations are we going to look for this time? So let's say we're looking for 3. Okay? We initialize them all as random matrices. And the recipe says first we should preserve the value of the oracle across the entire data set. So I'll put that in here. Okay, so I'm sorry. There we go. So the first recipe is that it must be invariant. So we sum across the value of the oracle across the entire data set. Next, you might notice that this one is pretty close to 0. So in this case, it didn't go all the way to 0, but sometimes when you have a hard problem, the easiest way to solve this is by looking for the loophole. The loophole in what I said, which is don't change the data set, is just to not change the data set. Or pardon me, to not change the oracle is not to change the data set. So you can have a trivial transformation, which would count as a symmetry so far. So we don't want to find just trivial transformations. So we're going to normalize them. So here's the normalized version. Now they're all normalized by convention. The sum of all the squares of these elements is 2. But that's it doesn't matter that it's 2. So now we can't just get around, we've closed the loophole of finding trivial transformations. But now we have the problem that sometimes you might just find copies of the same transformation. This is not interesting. What's the point in having 3 if they're all the same? So we add another condition, which is orthogonality. So when I impose this, they'll transform into some way which is orthogonal. So the way to read this is that they must leave the data the same, they must be non-trivial, and they must be different or distinct. Okay, and so we can also do one more thing. So this is already good enough, but for our purposes, we'd like to be able to interpret this thing. We would like these things to have a sparse representation. So we put a regularization term which corresponds to sparsity, which encourages that they have as few non-zero components as possible. And now we can actually retrieve the thing. This is how we got the thing that you were seeing on the first slide of this. This is the X rotation, the Y rotation, and the Z rotation. Or actually, sorry, this is the Z rotation. Okay, so now we found these sparse generators of symmetries, which are easily interpretable to be the things that we're used to seeing. We can add one more thing to our recipe, which is that they must be closed. This is a group theoretic requirement, which I'll get to this a little bit more in a second. Essentially, it means that any combination of two things gives you another thing that you already have. Okay, so orthogonality, we've seen how something, okay, so this is complete, this is training all three together. I'm gonna take something and I'm gonna train 3 uncorrelated generators, but they're kind of the same. You know, they're not that distinct. And you can see that in 3 dimensions, and because they're rotations, I can actually draw the axis about which they are rotations. So if I do that, you can see that they're kind of just random axes. But when I impose my orthogonality condition, I get this picture instead. Oh, so there's my orthogonality condition. And now here, you can see that as it trains, you get some nice orthonormal basis. They're like this, they're all 90 degrees roughly. One other thing is that I don't have a picture to show this, but there are some randomly oriented orthogonal bases. The sparsity causes them to orient to the axes. Okay. So the way to think about this is that the generator, it tells you at each point which way you should move to preserve the conserved quantity. So in this case, the conserved quantity looks like this. This is measuring how far I am from the origin, 0, 1, etc. And it says here, if I want to preserve that, I need to go in this direction. So you can think of this as a vector field, and the whole condition is that the vector field has to be aligned with these contours. Okay, we'll come back to that in just a second. So I want to talk for a moment about this closure condition. So this is where it gets pretty interesting from a mathematical perspective. So what we found is that if you specify a dimension, so this is rotations in 2 dimensions, you can try to train one generator, and plotted here as a function of epochs is the loss function, or the log of the loss function. So with one generator, that's the blue line, you train and it just goes down to 0. Okay, so you find the answer which is invariant and has all the conditions we wanted. The other things, the orthogonality, are trivial now. But with 2, you can't find them. You see that the loss function never goes down, which means you never find the answer. You never find an answer. And this corresponds to the fact that there's only one way to rotate in 2 dimensions. So we found the maximal group of rotations. If you go on to 3, 4, 5, etc., generators, it only gets worse. So you can tell that there's only a 1-dimensional symmetry. The Lie group of those symmetries is only rank 1. We can do the same thing in 3 dimensions. The story gets a little more interesting. With 1 generator, you can see it trains down to 0. 2 generators does not go down. And that's because if you have a rotation, say in the X and the rotation in the Y, if you do those one after another, and then you subtract the difference of doing it in the other order, that's called the Lie bracket. Basically, if you compose them, you end up with the Z rotation. So it turns out that these things do not form a closed group. So you're able to find the group structure. So if 1 works, 2 doesn't work, 3 works, and 4 doesn't work for the orthogonality reasons. Meaning that you only have 3 axes you can rotate around. If you try to add a 4th one, good luck finding a 4th orthogonal thing, which is orthogonal X, Y, and Z. So I'm drawing these as blue squares here. So you can see for 2 dimensions, we only have 1 generator. For 3 dimensions, there's 1 generator or 3 generators. So this is a subgroup of that. And we're able to find the group structure. When you get to 4 dimensions, we actually found a surprise. So, so you can try with all of these different numbers. So 1 works, 2, 3 work. I'll skip 4. 5 does not work. 6 works. Okay, so it turns out that you can do 6 generators, because essentially in this particular example, what's happening is you're choosing 2 out of 4 axes to rotate around. So choose 4 is 6. So that's why the maximal group has 6 things. There's a 3-generator subgroup, which is just, ignore the 4th dimension. And so you inherit this stuff. And you also get this now, which is an abelian subgroup. Here, we had a surprise. We didn't realize at the time we were running this that there was a 4-generator subgroup of SO4. And so when we trained it, we thought it was a mistake that this trained down to 0 loss. When we looked at it more, we found out that actually it had realized that there is a 4-generator subgroup. The generators look like this. It's not quite as obvious. So this is sort of like a non-trivial fact about group theory that our method told us about. So we were very excited to see that. Of course, this is a known thing. So this turns out to correspond to U3 cross U1, or SO3 cross SO2. Okay. So far we've been dealing only with the real matrices, preserving the length of a real vector. From a group theory and physics perspective, the interesting groups are actually these things called unitary groups. And they have the same behavior, except instead of preserving a real vector, they preserve a complex vector. So we just straightforwardly generalize everything. We can take as an example, we're looking at some complex vector. We parameterize the generator like this now. It's got real and imaginary components in the matrix. We draw that like this. Here's the real matrix, here's the imaginary component of the matrix. And then everything's the same except that we put an I here to follow conventions. Okay, so in 2 dimensions, we find this. When we run with 3 generators, we see these matrices. Does this look familiar to anyone? If you remember, the way to read these is that, it's okay. I think you're unmuted, somebody. So what does this look like? Does anyone recognize the polymatrices? So those are in fact the generators of SU2, especially unitary groups of 2 dimensions, and this is the generator of U1. So just by imposing the closure condition, we're able to get this. Let me just, there's anything I can do here.
Yeah, you can. Yeah, right there.
I don't see how to mute them.
I'll tell her.
Oh, it's okay. So, okay, so you can repeat this trick in 3 and 4 and 5 and 6 dimensions. In 3 dimensions, you get these things which might be familiar to physicists as the Gell-Mann matrices, and this is another version of that, which is just adding in the identity matrix and so on. But I will not talk more about these. So I want to get on to my last point, which is how to apply this. So earlier I said that we would generalize later to more complicated oracles than just the length of a vector. So if we take our oracle to be, say, a classifier output of some machine learning model, we can actually find symmetries of that thing too. So as my first non-trivial oracle, or less trivial oracle, I want to do the so-called L1 norm. So this is just the sum of the absolute value, or the absolute value of the sum of x and y. Actually, those should each have their own absolute values. The contours look like this, and you can see our old model, remember the vectors need to point along the contours. In this case, the vectors point along the contours here, but here they start to fail. These are not actually invariant. The linear transformation says you need to move in this way, but that's not actually along the contour, so it's not keeping anything invariant. So it's not a real symmetry. The real symmetry is like this. And by making the generator model more complicated, so remember I said I was initializing it as a linear layer with no bias. Just by giving it a bias, giving it an activation function, adding more layers, we're able to find this thing. So we're able to find these symmetries. Going back to our old recipe, this thing was already defined with reference only to the action on the data. These were defined with reference to the components of the matrix. We found that actually that was providing a natural metric to tell the norm of something and the orthogonality of these different generators. But we were able to come up with an alternative definition which instead looked at the action on the sample space. So looking at those vectors I was just showing you. So if we look at those vectors, add all the samples, we can average over them and force them to obey certain analogous conditions. And so when we were, okay, so before I get to this, I want to say that this sample space trick seems to work pretty well. It worked in this last example. But one thing I really wanted to do was apply it to images. And when we applied it to images, you might realize that the natural metric on images would be, say, essentially what we're talking about is like the mean squared difference between two images. So that will be very small for something like adding a pixel of noise somewhere, or just perturbing some values. But something like shifting the image by 1 pixel, this would be a very big distance in that metric. So since I had in mind some properties I wanted to be able to capture, I didn't think this metric would be suitable for finding these symmetries. So I figured that we could instead look at a metric in a latent space. So there's this thing in machine learning called an autoencoder, and what an autoencoder is where you take some image and you make a neural network where the output is the same size as the input. So you take in an image, you spit out an image, and then you train it with the loss function, which says, make this pixel the same as the pixel in the original image. So I train it across the whole data set, and it learns that whatever I put in, it should give me the same thing out. The catch is that it has to do this while being bottlenecked down. So here is maybe 784 numbers. In the middle, I have maybe only 8 numbers or something. So I have to be able to reproduce this huge image, which is really just a big list of numbers. But I'm only allowed to pass at some point through some smaller list of numbers. So I have to find a representation. So this whole part is called an encoder. So I encode the image in some nice way, and then I can decode the image. And so hopefully I found a good enough representation that allows me to do this with high fidelity. So this is very standard, so you can train this. And then our trick was that we just did the same thing as before, but the metric was the metric of this latent space. And so when we did this, we did it, of course, on MNIST, and these are these handwritten digits. And here are some of the symmetries that we found. So I'm going to now show one of we're starting at these digits, and now we're going to walk in the direction of one of these symmetries. So we were able to find this transformation, which essentially preserves some key features of these images. But it's in a sort of non-trivial way. And I should say here, to be clear, the oracle that we're using is the classifier output of a trained classifier. So this 5, and this 5, and this 5 all get classified the same way, which is to say like 99% 5, 1% such and such, 1% such and such. Okay, so they all, to the model, look the same. To us, maybe we say, oh, that's actually a little bit different. But to the model, this is what the model really learned. And if you keep walking, actually, in this direction, so we walk a little way and then we walk back, so we get this nice looping animation. But if you keep walking instead, you will eventually walk off a cliff into a region where there was no training data, and into a region where the model confidently predicts something which is, to us, looks like noise, but it says, oh, this is definitely a 5 or definitely a 1 or something. And this is a well-known problem of robustness, which is that neural networks are not robust. So my hope is that eventually we can, there can be an application for this in robustness. Okay, so that's everything I have to say in the talk. Let me just first thank you all for listening. I would like to thank especially a few people. My academic older brother, Prashant, who taught me everything I know. I'd like to thank Saranas and some other collaborators at UCF who were writing an Exoplanet paper with. I'd like to thank Sergey Gleiser and Pierre Ramon, of course. I'd like to thank all my friends in the department and my family. And of course, I'd like to thank my committee. This is straight out of the dissertation. But lastly, I'd especially like to thank my team, my wonderful advisor, and I guess I can't say co-advisor, but for reasons mentioned earlier, and my academic younger brothers, Roy and Yoop. So thank you all very much. So yeah, thank you for listening. If I can just actually add a couple of little things here. So I'd like to mention one other thing which connects two of the big topics that I talked about, symmetries and exoplanets. Just last week, I told you this is an addictive area of research, we keep finding new things. Yoop was able to rediscover some of the exoplanet degeneracies I was talking about earlier with the symmetries method. So it actually is not quite as disconnected as you might think. We're interested in doing, oh, okay, I'll leave this for later. So I'll hand it over to you.
So let's open the floor for questions. Let me first start with questions from the Zoom. Darren or Jeff, do you have any questions, comments?
I guess not for me. I mean, the earlier work that you skipped over was kind of more close, I guess, to me as an experimentalist in ING. But I guess maybe just as a general question, I mean, how do these approaches improve upon, I mean, you're using machine learning, but I guess in what I'm thinking and trying to tease things out of data, trends and stuff, I use likelihood functions or things like that. So can you encapsulate why the machine learning is maybe better than other approaches that are more statistical in nature or something when you're looking at trends in data?
The transit data?
Any data, yeah, it could be transit data.
Oh, it trends in data.
Trends, yeah.
I don't think it's necessarily better. I think there's just some cases where the relation, I mean, so I think that this is the view that a lot of people have, that like the way to do, you know, sophisticated research is to have a sophisticated deep learning model. And I think a lot of our research is actually focused on avoiding that as much as possible. We've sometimes joked that we do anti-machine learning research, where we're essentially trying to figure out ways of processing the data which don't use deep learning as much as we possibly can, because we think it's more interpretable and we think that we can use our inductive biases and our domain knowledge better. And then I think the only role for deep learning is when you have something that's like a truly complicated map, like something like you have really complicated data like images. You know, you're not gonna, people have tried for many years to do GeoFAI methods of, you know, writing down a function which classifies an image, and we just know empirically that that doesn't work as well as the deep learning approach.
Okay, yeah, that makes sense. So you're basically trying to, as you say, the interpretation, find as few ways to describe, say, the symmetries of the problem or something.
I guess
Whereas
essentially,
if I was doing an analysis, I wouldn't necessarily know what might be those symmetries. I guess you use.
yeah, and I mean, there's a lot of work
them.
that's done on trying to find that. That might be itself an interpretability question, like what are like feature importance or something. Yeah, essentially I don't agree with the premise, which is that we think that machine learning is like inherently superior to statistical methods. Like they're all just alternative, you know, things in your toolbox.
I guess what you're saying is, yeah, you can be a bit smarter, so you don't have to do the brute force, full deep learning, and be completely, you know, agnostic about any knowledge.
And if I can
mention agnostic, so he's asking in his data, he doesn't know what symmetries are. Does this method work? Is it agnostic?
Yeah, this method is agnostic. Yeah, you don't need to know in advance. So I've been showing most of the time rotations, which obviously we have a very good understanding of, like both intuitively and group theoretically. This is like a well-studied group, but like the point is we want to do everything in a way which is agnostic to the actual structure. Because if it's not agnostic, then all we've found is a clever way of saying something we already know, which is that rotation groups are this way. Yeah.
No, it's pretty good. Yeah.
Yeah, and so, yeah, this question of domain knowledge, I think this thing nicely just point this out again. Yeah. Like, yes, I think it does help to do it the simpler way rather than just the hammer. Should we take questions from the audience?
Jeff,
Should we do audience questions before?
okay, let's open the floor to questions from the audience.
I guess I got a question, and that's,
Yes.
well, it just has to do with where is this going to take you, take it next? I mean, where can you apply these methods to? What I mean, you particle physics, exoplanets. What else can you apply these techniques to?
Right.
I mean, climate change, like what? I mean,
Yeah.
what other difficult problems could this solve?
Right, yeah. So here in my future work, I'm talking about a lot of stuff which is very specific to this kind of group theory stuff, but my hope, so here I've included a couple things which are more broadly useful kinds of things. Like maybe there's a way to sort of turn this around. Instead of just interpreting models, you say, oh, the model has a symmetry. You say, we want the model to have this symmetry. So it might actually be able to help improve the robustness or interpretability of models. And that's useful for, I would say anywhere that machine learning is useful, it's better to have, improve how well you understand the thing and how robust it is. I mean, that's kind of a lofty goal. I don't think this research alone would, I'm not making quite such a broad claim. Of course, I think it's really useful to understand what your model's doing in case it does bad things. Interpretability is super useful for fairness and control. Yeah, this doesn't really answer your question. The last part C doesn't really answer your question.
Like what other large data sets that you would apply this to?
Do you mean that would be useful to the world?
Yeah, right.
Or?
Rather than exoplanet atmospheres.
Yeah, so it's all about trying to give you more addictive YouTube recommendations. So you can't stop watching YouTube, or so you can't resist the thing the advertiser served you on Amazon.
Right.
That's the real use case.
Don't
yeah.
do it all.
Thanks a lot.
Yeah, I would say I'm more interested in developing the technology rather than the specific applications. But of course, hopefully it'll someday be applied to something useful. But I think there's a pretty clear path from making machine learning better to applying it usefully, unlike some other things I might work on.
Which paper was it that ended up on NASA's homepage?
I should have shown that.
Yeah.
That was
Exoplanet sifting
which
data.
exoplanet paper ended up? That was the first one. That was the degeneracies one that I have shown.
Yeah.
I think there's a question on Zoom.
Ioannis is asking a question.
Giannis, do you have a question?
Can you hear me?
Yes.
Well, first of all, this is amazing work. I was thinking about types of data sets in which an approach that discovers symmetry could be useful. So, I want to understand whether something like that would work with what you have here. So, suppose that you have a data set of planet trajectories, stellar ocean trajectories. And we know about the symmetries of problems. And let's say in the standard theory of Newtonian gravity, there is this obscure vector, the Runge-Lenz vector,
Yes.
that is a conserved quantity there.
It's so funny you mentioned this because Andrew Davis and I were just talking about the Laplace-Runge-Lorentz vector and would it be possible to find this symmetry? I was just thinking about that the other day. I was just talking. That's so funny that you mentioned that. Yeah, I think.
So what I was thinking in terms of that, of course there is this vector, and we know that exists there. But maybe you could extend this a little bit further and say, okay, now I take an alternative, a modified version of gravity, and then I try to find whether there are similar conserved quantities there that are as obscure as that.
Yeah, I think that would be amazing. So first of all, I would say that the work we're doing here, actually what it does is it takes a conserved quantity and finds the generators of symmetries. However, This is very cool, but it's sort of limited in that you have to know in advance what is the thing you want to conserve, or have a model which predicts the thing you want to conserve, like in the case of the digits. So the original work that inspired this actually did not make a reference to conserved quantities, and it proposed what they call the symmetry GAN. Recently, we've been talking more about doing more stuff on this, where the thing you're trying to preserve is the probability distribution function of the data. So
it's unsupervised.
It's unsupervised, thank you. Yeah, so I think that what we have here would not do what you're asking, but this other thing that we're working towards, this unsupervised approach, this may be possible. I would have to think about the exact problem and if it's actually conserving a distribution. Yeah, but I think that would be like an amazing like holy grail of this kind of symmetry discovery work, to like find a new symmetry people haven't known about.
Yeah.
So currently we're doing it supervised, and so we need
currently
a
it's
label.
supervised.
But it can be applied to any
Well,
label based.
I would say actually the symmetries of the digits are not supervised, because we train a model. Oh, actually, no, sorry, they are supervised. Yeah. You?
Do you think in future will it be possible to learn these symmetries, then use those symmetries as constraints on your machine learning model to make them commerce faster?
This is something. Oh, to make them like faster, rather than just more
converging
robust.
faster and learning better.
Yeah, I would hope. I mean, that would be amazing. I can't confidently say that, but I think that would be a really good goal to work towards. Yeah, I think the symmetry stuff is very interesting, and I think that the overall idea of putting more rigorous mathematical framework in machine learning, where you really can like better understand these things, or have I mean, what a cool regularization to have, right? Symmetry regularization. Like, my model approximately learned the symmetry, I identify it as approximate, and I constrain it to be exact. That's a very like non-trivial kind of thing to regularize in your model, and I don't know. I would be very excited if that worked. So.
Yes, we're working toward. That's part of your thesis.
Yes, that'll be your thesis. That's right.
So let me be the bogeyman trying to defend machine learning for you then. You've been talking about symmetries because we as humanity have knowledge of symmetries. Right? So I'll show you this other domain where we seem to have a half-baked model, and for 200 years we have not managed to fully bake it. And the domain is natural language processing.
Yeah.
Okay? For the longest time in history, people have been trying to come up with grammatical rules that will define whether a sentence is grammatically correct or not. And it's been going on, and for so many years we have tried, we've never managed to do it. Look at what ChatGPT does. So it is this massive network that has been given all the so-called grammatically correct sentences, and it seems to have figured it out.
Yeah.
And yet, it helps us in no way, except that ChatGPT does what it does.
Yeah.
It has not improved our knowledge. So where is the stuff that you're talking about? How is it going to improve knowledge? Things we already know, we can put into the machine. I completely agree. But things we do not know, as Rumsfeld said, there are knowns, there are unknowns, and then there are unknown unknowns. A lot of machine learning is about these unknown unknowns. We are essentially not being able to make progress understanding the true model, because if we did have a true model, we would not need a deep network. So the big question then is, where is this boundary? How far can you push these to be able to actually produce new knowledge? I don't even know whether there's a question in there.
Yeah, I just agree with everything you said. Yeah, I don't think I know the answer to that question, first of all. Like,
So is there something that you can see where you can use machine learning to produce new knowledge? The kind of stuff you showed, right? These symmetries.
It's old knowledge.
It's old knowledge.
Yes.
Not the exoplanet degeneracies. If we had done
Yes.
those projects in the reverse order, then Ayub would have found the degeneracies.
And we would have said, whoa, there's degeneracies? Yeah, I think as soon as I figure out an answer, I'm going to go write a paper on it. So if you have any suggestions, I think that would be really exciting. Yeah. Like one thing I would kind of like very ambitiously compare this to is I don't want to commit the sin of like comparing yourself to something amazing, but the alpha tensor from DeepMind, it's not the same thing at all. But this thing was essentially trained by reinforcement learning to do a certain task, and it was able to find new knowledge, something that beat the Strawson algorithm for matrix multiplication, and it was able to actually make systems faster. Like that's new knowledge discovered by the machine. I would say when we figured out that there was a 4-generator subgroup of SO4, this feels like the baby version of that to me. Because number one, it's already known, unfortunately. I wish the group theorists had not worked so hard. Why did you have to figure everything out already in the group theory? But you know, it did tell us something that we didn't put in, even if it had already been found out by other people. And I thought that was pretty exciting. So it's essentially rearranging things that we did put in, of course, but in a way that we hadn't appreciated.
People who play good chess, I'm nowhere close to playing even decent chess.
Mm-hmm.
But I know kids who play extremely good chess, were saying that these machines are producing new chess knowledge.
We had a project about that.
Yeah, Dr.
Yeah, so I have 2 questions. One of them, have you encountered and built the Platonic solids from this?
No. You mean the symmetries of the Platonic solids?
Yeah, I mean, there are 5 Platonic solids, right? And we don't know a priori that they're there.
Right.
I mean, even though the Greeks knew them.
So I think
And the question is, can you come up? And I see that you're going on the exceptional groups over there, which are in one-to-one correspondence with Platonic solids.
So then the answer is yes, because we can do those properties.
Well, so you should be able to.
Yes,
You
the
should.
answer is yes.
Number 1. Number 2, if I look at your 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you look at different handwritings of people for those digits, presumably there must be a class of these deformations. Do they correspond to something that, if you take 1,000 people writing down those, do they look at all like this or not?
Do you mean if I take different people's handwritings that are like basically different points in the space?
Yeah, in other words, are the different handwriting, can they put in a different class? And some classes may look a lot like this, or some may not. Is there a way of, I'm not sure there is a way, but you know.
A way of doing what?
Well, the question is that, you know, you have, these are definitely, appear like deformations, right?
Mm-hmm.
Okay. Now, so most people, when they write the integers, okay, they basically do not write the whole thing, but they write something. So if you look at this particular thing and then you compare with, for example, 10,000 people writing these, etc., is there any organization in other words? This is one particular type of organization.
So, if I understand correctly, so yeah, you take 10,000 different people and ask how did they all write 2s and how did they all write 3s, you get a bunch of, I would say those correspond to different points in the latent space. That's the way
I know.
Right?
I understand that.
And they're clustered.
But the question is simply
Hopefully.
that, you know, so it goes back to another thing, which is that, I forget the name of the Russian mathematician, but there is a question of building not rigid lattices. There's a science to this.
Okay.
Okay? And you can build structures which are forbidden by, but then you can build, if you can bend the rods or something like this, and there is a systematic to that.
Mm-hmm.
Have you heard of this?
I've never heard of this.
Okay, I will try to
Okay, we should go.
To fish it out, that's what Russian mathematicians do in the winter.
Too much vodka.
Any other questions?
I have a question. So the symmetry GANs, are they, is it a generative model?
Is it a generative model?
Like, does it,
Let me think for a
like, do you
second.
impose a symmetry and like get things that preserve the symmetry, or?
Let me think for a sec. So the original conception of the symmetry GAN was that you would have a. Let me think. Yeah. So the generator is the generator of symmetries. So what it does is it produces a generator of symmetries in this way. Yeah. So the generator is not what you're thinking of, where I put in just garbage and I get out some like nice picture or something. It's more like I put in data and I get the transformed data. Does that answer your question?
Yeah.
Symmetry again, you mean the Jesse's?
Yeah, here, yeah, so here I'm using it a little loosely. I'm not saying specifically Jesse, I'm saying the idea that Jesse was pointing to.
Their thing was called symmetry.
Yeah, their thing is called symmetry, yeah.
Is it just a GAN that's informed by symmetries? But like, does it generate new stuff, or does it just generate rotated stuff?
So it's a generative model that generates from some probability distribution.
Yeah.
And then the symmetry
Yeah.
you
It's just
can apply on the probability distribution
So,
But like, can it?
so what I would say is that basically, so a normal GAN would work like this, okay? I have some noise and I take this to some data, which is hopefully similar to my old data set.
That
Okay?
is
Yeah. So I have some noise and I have a generator model, and then I have this produces some data set. I shouldn't use E, but and I have some discriminator which looks at these. This is an ordinary one. What I have here is this is my generator model, which takes something, acts as symmetry on them to get the transformed thing. And then here I have a copy of the, more or less the original thing, and I have a discriminator which says, are these things the same? So the difference is that these are all the same in kind. Here, this was just some latent noise, and these were the same in kind. So that's the idea, essentially. This is proposed by this guy, Jesse Taylor. This is not our thing. But I like it. I like the general idea of it. And I think it's cool to, in particular, what this thing is, he doesn't really train a discriminator. He just says that these things have to have the same distribution.
Thank you.
So, did that answer your question? What was your original question?
No, I think it.
Yeah, so it's not just an ordinary GAN. It's doing something a little different.
Yeah, I get you.
But it has the same flavor.
But like, in terms of interpretability, like, can you actually get out a symmetry from this GAN? Like, if I wanted to learn a symmetry, like, could you get out a group like that? So you can. Like, do you see what I'm saying?
Oh, so it doesn't tell you.
Like, yours can kind of like figure out a Lie group. Almost.
Yeah, no,
Like,
that's something that ours is better
Yeah.
at. Yeah. No, theirs will just tell you asymmetry. It
Yeah,
won't
yeah,
tell you
yeah.
multiple, and it won't tell you their group structure.
Right.
No, that's right. No, that's something that we wanted to do. We saw the opportunity to do that differently and get this cool structure.
Mm-hmm.
So, essentially, if you gave it something that has a lot of symmetry, like a sphere, like data on a sphere, it would just give you some random rotation of the
Yeah.
sphere. That would be the generator that it would find.
Mm-hmm.
I pretty much guarantee it. And we would say, let me vary the number of generators and impose all these other constraints, and then we're going to see the algebra that comes out of that and identify it.
Mm-hmm.
So, but we have to have an oracle. So now the next thing is to take the best of both worlds. No oracle, so totally unsupervised, and our things, and put them together, and that's something I want to do next.
Are you going to can you find supersymmetry?
We're thinking about it. Should be, we're thinking about it. No more questions? Last chance for questions from Zoom.
Let me check on Zoom.
I just want to say, Alex, I really enjoyed the presentation. Yeah, you should be pretty proud of what you've done.
Thanks, Jeff. Thank you.
All right, so in that case, the standard procedure is we ask everybody but the committee to leave, and then we'll grill him, behind closed doors.
But grab a donut on your way out.
Sorry.
Grab a
Safe
donut
days.
on the way out.